Good morning, everybody. It's 11:10 now, so welcome. I'm going to get right into things since got a lot of questions about last night's assessment. Then I'm going to start in on chapter 4, talking about 2D vectors, breaking vectors, force vectors into their components, and Newton's second law in 2D. We'll be talking about tension and pulleys as well. So this is the histogram for last night's midterm. So it was just 10 multiple choice questions. And it was marked automatically. And we'll go over those now. So everyone just got something out of 10, and to make it out of 100, each question was 10 points. So in fact, 142 people got 100%. The average was 74. There has never, as in my knowledge, been a Physics 131 midterm with this high of an average. Normally my tests come out to be around 50, between 50 and 60, like around 55% average, and then sometimes there's a boost up to 65%. But the average is 74%, which is fantastic. 53% of the class got A's on this. So there you go. So that's great. You know, I'll have to explain it to my boss, but I think it's okay. I think we should just just leave it. It was a weird format. I think there was a lot of glitches that happened with some people, internet glitches and stuff, and I empathize with that. Let me just go to the chat window. I think it might be useful to just go through some of the questions and talk about them. I can take a quick look at the chat though. And certainly, I completely agree that having a multiple choice format where there's no opportunity to show your work and get partial credit for laying things out in the solution format is a problem. So I don't know how I'm going to do it, but I would like to try some different kinds of formats for these assessments. So the October 12th one, I think I'm going to try to do some kind of a written submission, but again, keep your eye open for that. I'll send out some instructions about that as we get closer. Okay. Let's talk about these multiple choice questions. This was the Angry Bird one. So I'm just showing them in the order that I wrote them, which is not necessarily the order that you wrote them in. So it says Angry Bird 1, so we'll call this guy number 1, is thrown upwards. So his V1 initial is up. And then Angry Bird 2 is released from rest. So V2 initial equals 0. So what will happen is that this guy will go up, and then at some point V1 equals 0, and then it'll go down here, and V1 will be negative, if you define up to be positive. And there's this one will just be V2 is negative. And what happens is it's constant acceleration. So A sub y is negative 9.8 meters per second is the slope. So they all have this constant downward slope. So that rules out pretty much a lot of these. The only ones left is D or C. So with D, it's seeing that they all have negative, whereas I think the Angry Bird 1 should start off positive and then go negative. So I like C. Lillian is pushing a box across the floor towards the front of the room. At the same time, Kevin is trying to stop the box by pushing it in the opposite direction. So I've tried to kind of draw the velocity is constant towards the right here. There's Kevin pushing to the left, Lillian pushing towards the right, friction pushing towards the left. So if you draw the force diagram on the box, you've got the F of K on the box. You've got the F of Lillian on the box, and then you've got the friction. And call that little friction or something like that. And so if you do the sum of all the forces, the F net or something like that, sum of the forces, and you say that it's not accelerating, so 0 acceleration, because it's constant velocity, then they have to sum up to be 0. And so the force that Lillian is pressing with is equal to the force that Kevin's pressing with, plus the friction. So it's going to be greater. Your car won't start, so you're pushing it. You apply a horizontal force of 30 newtons, but it doesn't move. What's the other force in the interaction pair? So this is if 1 equals U and 2 equals the car, then F of 1 on 2 is equal to 300 newtons. So this is Newton's third law. Says F1 on 2 equals F2 on 1. This is the force of car on U. Okay. There's a lot of other forces going on, but none of them are the other one in the interaction pair. Well, I guess so someone asked, why does the friction act only in one direction? So yeah, the friction, I'm just thinking that there is friction between the box and the floor. That's going to be, we didn't really talk about this too much, but I think the idea is that if you're sliding along, the friction opposes the motion, opposes the velocity. Okay. So here is an object moves along the x-axis whose velocity versus time graph is shown. What is the displacement? So what you do is the area under the v versus t plot gives the displacement. And the way I did this, a few ways of doing it, is that I looked at this region right here, that triangle and this triangle. This is a negative triangle and this is a positive triangle. So I would say they cancel each other out. Positive, negative. They sum to 0. So between 4 seconds and 8 seconds, there's no, you're going forward as much as you're going backwards, there's no displacement. So the only real thing from going from 3 seconds, which is about here, to 8 seconds is just going to be the area of this rectangle here. So that's going to be 1 second times 20, and you're going to get 1 second of 20 meters per second, you get 20 meters. This is that vector addition one. I just showed you 3 vectors. So what I did is I just connected them head to tail. So A goes to there, B goes down 4 to this point, and then C goes over to the left. So that it's a little hard to see there, but the actual sum of these forces is going to be this to the right and 1 Newton in length. Okay, and of course, some people are saying they got different answers. This is all from the first sitting, the 8 p.m. sitting. The people at the 10 p.m. sitting, you would have got different questions. So, okay, you walked 3/4 of the way to school, so 3/4 of the distance. Okay, 3/4 of distance, not the time, I guess. At a speed of 1.3 meters per second, and you ran the final quarter at a speed of 2.7 meters per second. What was your average speed? So, so this is your basic equation for not accelerating, is v is d over t, t equals d over v. So there's the walking time and the running time, and the total time is going to be your time walking plus your time running. So your average speed is going to be the total distance divided by the total time. So when you're walking, t equals d over v, The distance is 0.75 of the total distance, divided by 1.3 meters per second. And when you're running, you've gone 0.25 of the total distance divided by your speed is 2.7. So I just set up those two equations and then plug them in, take these and plug them into this equation. And then the D's all cancel. D's cancel, which is lucky since they didn't tell you the whole distance. And then you just do that math, and I eventually got 1.49 meters per second. So you definitely needed a calculator for that one. A juggler throws a bowling pin straight up with an initial speed of 7.7 meters per second. How much time elapses until the bowling pin returns to the juggler's hand? So this one's got a V1, which is given, and then a V2. So what I'm thinking is that there's sort of a symmetry. On the way up, you're decelerating at 9.8 meters per second squared. And on the way down, you're accelerating the same distance at 9.8 meters per second squared. So when you reach the same vertical position, you're going to be going down with the same speed that you started going up. We discussed this a few times in class, but it's sort of like this: what goes up must come down. You go up, slowing down, you come down, speeding up, and because that motion's symmetric, the final velocity is just negative of the initial velocity. So V2 equals negative V1. And then I'm just going to use that the change in velocity is equal to the acceleration times the time. This is coming from, I guess, delta V is equal, in the y direction, I guess, is a sub y times t. Okay. And a sub y is a negative g, where g is 9.8. So then I solve for t, because that's what you're asked for. And then V1 minus V2 is just V1 minus V1. So you get 2 V1. Does that make sense? So delta V1 minus V2 equals V1 minus V1 is equal to, 2 V1. So that's where that comes from. So it's 2 times 7.75 divided by 1.582 seconds. Yeah, and then Lynn asked for question 7, can you figure out the time used to reach the top and then multiply that by 2? Yeah, absolutely. There's a lot of ways to get this 1.58 seconds. This was just the way that I chose to do it. But yeah, you could just make the final velocity 0. You would calculate it, you would get half of that. See if I can turn it on by throwing an Angry Bird. No, I have to take one. Okay, it is the future and you have just landed on a distant planet called Planet X. You release a ball of mass m equals 0.1 kilograms from rest at a height of 10 meters and measure that it takes 3.4 seconds for it to reach the ground. There is no air on Planet X, so you can neglect the air resistance. Hopefully you've got a spacesuit on or something. What is the magnitude of the gravitational force of Planet X on the ball? So yeah, the basic idea here is that it's free fall. And so you've got a force on it, which is just the whole sum of all the forces is equal to m times g, whatever g is in that environment, fg. So you start with an initial velocity 0, you go down to distance 10 meters, it takes 3.4 seconds. The equation that seems to be a good one for this one is that v equals, you're going to use x is equal to x0 plus v0 t plus 1/2 at squared. But this v0 is 0. We're going to set that equal to 0. So just get d equals 1/2 at squared. And then solve it out for a, and the force of gravity is mass times this acceleration, I guess. Does that make sense? The net force. guys did pretty well on that one. So. A rock is tossed straight up with an initial speed of 25 meters per second. When it returns, it falls into a deep hole. The bottom of the hole is 8 meters below the initial position of the rock. What is the rock speed just before it hits the bottom of the hole? So I'm sketching that out as you've got some V initial. I'm going to set plus Y is up. You've got Y final down here. Y final minus Y initial is -8 meters because it goes up and then comes back down. A sub Y is down, -9.8. And it's asking for what is the final velocity. So this is one where you're going to use that equation that does not have the time and just solve out for V final. And what's interesting is it doesn't matter that it was going up and coming down. You just use it the initial position, and then the final position is 8 meters below it. Anyway, and you get 28 meters per second. And last question. A cart of mass 500 kilograms is rolling with a speed of 5 meters per second on a railway track. There's very little friction between the tracks and the cart. You apply a constant force on the cart in the direction opposite to the velocity. From the moment you start applying the force, the cart moves a distance of 30 meters before coming to a stop. Okay, so the sum of the forces is MA. So what I think is happening is you've got, here's your cart, it's going along, and the sort of force diagram, there must be a normal force and mg, but you're applying this external force F, and that's what you're trying to find. Find this. And so what you need is the net force is equal to the F, okay? And you need to find the acceleration. We know the final speed is 0 because it stops. We know the initial speed was 5 meters per second. We don't know the acceleration because it's this horizontal thing, but we know the distance that it traveled. So, and we don't seem to care about the time that it took. So once again, I'm going to use this equation that does not have time and solve it out for the acceleration. And then the force will be mass times that acceleration. That's the needed force. So 500 times this acceleration. I ended up with actually 208, which wasn't really in the list, but it's sort of what is the approximate magnitude of the force? Closest answer is 200. Okay. I think I got 28 for that one. Just looking at some of the chat window stuff. And we can look at hands up. So, and when the hands are up, so what I want to talk about right now during the lecture are like general things that are of interest to everybody. And I know a lot of you have so many like things on your mind that you want to talk to me about that are specific to what happened to you on your quiz. And I do want to talk to you about that stuff, but just not during the whole class lecture, if that makes sense. So I've got time in my office hours after this. I will be going on my emails. I'm, to try to address any issues that you have that are personal to you. But just so right now, do you have any questions that are kind of more general or about the physics here in any of these problems? Because if so, I would like to hear from you. And Bardia, did you have any question?
Hi, sir. Can you hear me?
Yeah, I can. Yeah.
Okay, I have a question about the one that you just saw, the one that you push the car,
Yeah.
and it says like what is another force that is pushing against the whole system is preventing the car from moving. Isn't it the friction force of the ground to the car that is preventing the car from moving? Because I think it's asking for that one.
The one that's on the screen right now, the cart of mass 500 kilograms?
No. The one that you as a person push against the car. I think it was the third question. I'm not sure.
Oh, okay. That I did? I forget which one you're talking about. Oh, yeah, this one. Yeah. Sorry.
Yeah, this
So,
one. Yeah.
Right, yeah, the reason it doesn't move, yeah, that's exactly right. So the reason it doesn't move is because the frictional force of the road on the car is equal and opposite to the force that you're pushing on the car. So actually, Marty, that's a really good point. They're equal and opposite. So this is a more of a philosophical question. I'm glad you brought it up. It's just because two forces are equal and opposite does not mean that they're two forces in an interaction pair. Another example would be me standing on the table. There's a normal force upwards on me that's equal and opposite to the gravity force downwards on me. Those are going to cancel each other, and that's why I don't accelerate. But the fact that they cancel each other is not the reason that is not because of Newton's third law. They're not forced to be equal and opposite. Okay, so like for example, if there was less friction, if you know, it is possible to push a car, right? The friction force is not always, by Newton's third law, equal and opposite to the pushing force. Okay, that's what's going on here. What is always equal and opposite is that the force that I push on the car is equal and opposite to the force that it pushes on me. That's fundamental. That's Newton's third law. In this particular situation, there's another force which is equal and opposite, but it's more by coincidence than by Newton's third law. I hope that helps. Liam, did you have a question?
Hi, Professor.
Hi.
Can you hear me okay?
Yeah, I can, yeah.
Yeah, so I just had a question about number 6. Would you be able to go over to it for a second?
Absolutely. Yeah, this one?
Yeah, so the way that I went about solving this was a little bit different, and
Okay.
I got a wrong answer, but I'm just wondering, like the way that I went about it was by finding the mean of like 4 separate sections of the velocity. So I did like 1.3 plus 1.3 plus 1.3 plus 2.7 all divided by 4.
Yeah.
And then that gives you 6.6 over 4, which is like 1.65. So I picked 1.7 for this, but that was not the right answer. So is that just like not a good way of solving this problem, or what's wrong?
Yeah, so it's not the correct way of solving it. What you have to do, I think what's going on probably is that your assumption somehow there is that he's going to spend as much time running, like a quarter of the time running. I think that's probably the assumption. And then the rest of the 3/4 of the time they'll spend walking. But in reality, I think you spend very little time actually running. So you just weighted the walking a little too much. It's not a bad idea, and it wasn't very far from the answer, but really what you have to do, I think, is use this idea of average velocity. You need the total distance divided by the total time. You have to sum up the times.
Okay, so with that sort of approach would only work if I knew that he, or that you spent the same amount of time in each velocity. So like if it was like 10 seconds at the first velocity, and then again, and then 10 seconds at 2.7, would then that be an okay way of solving that? Or
yeah, I think so, because then what you're doing is you're weighting the different times, same as what we're doing here.
Okay, that makes sense. Thank you very much.
Yeah, you're welcome. All right. Okay, so I think probably what I should do is start to move on here. I look at my notes. I do want to start talking about chapter 4 stuff. This is Newton's second law in component form. So what we're doing is we're going into 2 dimensions now. And this is the idea of this whole thing here, is that maybe you have an object. Let's do a force diagram. Let's actually use that. And let's draw a force diagram of object S, okay? And 3 external objects, influences, or things, let's call them things, are exerting forces. Sorry about handwriting here. Forces on S. And let's just say it sort of looks like this. You might have F1 on S. Maybe that's a diagonal force. Sometimes you might draw even like theta or something. You have downward F2 on S. This could be gravity, for example, and the object 2 could be the Earth. And then let's do F3 on S. So just for example. Well, what you would do to use Newton's second law is you could define up to be y, to the right to be x, and then you can find all the components. So I tend to do a little chart where I say, okay, here's the forces, here's the x component, here's the y component, and here's all the forces. So the forces are going to be F1 on S, F2 on S, and F3 on S. Well, the easy ones actually are the ones that are not on the diagonal. So the F3 on S, it's got a negative F3 on S, or I'm just going to call it F3, just to kind of save all the writing here. Negative F3, and then 0. It's going in the negative x direction, so the y component is 0, the x component is negative. And then F2 on S, which might be the gravity, for example, that has a 0 x component, and we're going to call that positive, or sorry, negative again, F2, because it's going in the down or minus y direction. And then this one for the F1, you have to draw a little triangle. I'm always drawing these little triangles. This is F1 in the y direction. This is F1 in the x direction. And then you have to do your whole SOHCAHTOA thing. So like sine theta is F1 y over F1. And cosine theta is F1 x over F1, right? So you do that little triangle, and what you end up with is you get F1 cos theta is the x component, and F1 sine theta is the y component. And then you can sum those all up if you want. The sum of the forces, which is what we're trying to find here for these acceleration equations, is going to be F1 cos theta minus F3, and the sum of the y components is going to be F1 cos sine theta minus F2. So then the acceleration in the of S in the x direction is going to be F1 cos theta minus F3, all divided by the mass. And the y acceleration is going to be F1 sine theta minus F2, all over n. So that's sort of an example given that, that diagram. So I think when you actually work out problems, you'll get a little bit more adept at writing these things. Let's do a little poll, shall we, since we haven't done one of those yet. A string is attached to the rearview mirror of a car. A ball is hanging on the other end of the string. The car is accelerating to the left in this diagram. Let me just draw that. Here's acceleration. And you're kind of in the car. Which of the following lists gives all of the forces directly acting on the ball? So we're going to draw a force diagram of this ball. And in order to draw a force diagram, you have to draw all the forces acting on the ball. No more, no less. So which of these? A is tension, B is tension, gravity, and a drag force from the air. C is tension and gravity. D is tension, gravity, and a fictitious force to the right. And think about which are the ones you're going to draw in your force diagram of the ball. Okay. Ideally, it'd be good to go to your practicals team and actually discuss this question right now, but I'm going to give you 5 seconds. 3, 4, 5. Show answers here. This one was a pretty controversial question. So no one thought there was just tension. There's definitely also gravity acting on this ball. But why is it off to the right? I actually completely agree with 42% of you who answered C. This is what I think the answer is. These are the only 2 forces that I would draw on this. So first of all, inside the car, there is very little wind. Does that make sense? Especially if all the windows are closed. Windows are closed. But I don't know if you've ever seen this. If you got something hanging from your rear view mirror, it does bend out. And it's not due to the drag force from the air, because there's not that much wind to be doing that. It's more its own inertia. And then the thing about these fictitious forces is that we don't use these. In this course. That's why I don't like that one. You shouldn't draw those. So the reason I don't like B is because I think that inside the car, there's probably not a lot of wind. If you thought B, it's understandable, but I just think that that's really not the reason here. The thing's accelerating, and that's the reason you've got this. And then fictitious forces, you shouldn't draw those. So what I'm going to do is I'm going to draw tension up like that, and this force down, F sub G is equal to mg. And that's all you need to draw on your force diagram. You shouldn't draw anything else. And then what you can do is you can do your little x and your y components. Once again, we can define, actually, why don't I define y to be up and x to be to the left, just so that the acceleration a sub x is positive. Because I've defined x to the left, which is okay to do. The 2 forces are tension and F sub G, the gravity. So the x component of the tension, oh, I have to do that triangle. This is annoying. So let's do a triangle. There's tension. There's your theta. There's your T sub x. There's your T sub y. There's your right angle. Again, I can never figure these things out. Sine theta is opposite, so that's Tx over T, and cos theta. Some people are really good at figuring things out in your head, but I always have to write out the triangles. Okay, so you solve out for Tx, it's going to be T times sine of theta, and then the y is going to be T times cos of theta, and the x component of gravity is 0. The y component of gravity is going to be your negative mg, because I defined plus y as up. That's going to work. And then, yeah, so then the a sub x, which is that acceleration, is going to be t sine theta divided by the mass of the ball. And a sub y, which is going to be 0, because it's not accelerating up or down, is equal to t cos theta minus mg divided by the mass. Something like that. Those are your equations there. But it wouldn't be accelerating unless there was an unbalanced x force. And if you add any of the other forces, you won't get it right. I know what's going on next here. Victoria, would you like to unmute? Just looking at raised hands here.
Hello, can you hear me?
Yes, I can.
Okay, perfect. Sorry, I was talking to myself. I didn't realize I was still on mute. So I said I had a question about the midterm. It was number 9, but now that we're on this, I guess I'll just first ask about this, and maybe later I can ask about the other one. In terms of this, I'm just kind of curious. When do we? I guess I'm trying to wrap my head around when is it that we don't we take out drag force, because when I was thinking of this scenario, I was thinking, okay, well, there has to be drag force because, I mean, what's pushing it this way? Maybe the window is open, even though it wasn't stated there. So when do we know, like, okay, drag force is definitely not present, like we have to rule that out?
Yeah, that's a really good question. I don't think you really do know. I would say that ruling out the drag force is more one of the assumptions you do in your sort of simplify and diagram phase. There might be drag force. You might be absolutely right. The window might be open. There might be a drag force. So it's either something that's going to be stated in the problem, neglect drag force from the air, or it's something that you can assume. And if you'll bear with me, I think that you have to kind of be plowing through some fluid. I think of the air as being this big static fluid, right? And if you're pushing through the air, then you will experience drag force. But if something's hanging from your rearview mirror in your car and it swings out, it's not really pushing through that air, because I think the windows are closed.
Yeah, okay.
More like an assumption. And Victoria, can I take your question about the midterm just after the class?
Yes, should I raise my hand again or just leave it?
Yeah, definitely. I'll look for you in there, but yeah, as soon as the class is over, I'll try to take your question first.
Okay.
And also, one more person was Siddharth. Did you have a question?
Hey, Professor.
Hey.
I had a quick question about the midterm. Would you mind just telling us, like, what is an ABC in terms of the quiz here?
Say that again, please.
Hi, can you hear me?
I can hear you. You said something about what is ABC.
Yeah, so what do you define in terms of the percentages as an ABC?
Oh, I see. Sorry. Yeah, I get you. Yeah, so what that is, that's in your academic, there's some sort of, in the calendar for U of T, which is online, there's all these guidelines. And so anything from 80 to 100 is considered an A. Anything from 70 to, I guess, 79 is considered a B. 60 to 69 is considered a C. D is 50 to 59, and 0 to 49 is considered an F. So that's where that's coming from. And okay, I think I'm going to continue going on. I wanted to talk about a couple more things today. One of them is this. I think that Atkina doesn't do such a good job introducing the ropes and the pulleys. They just sort of come out naturally. She starts using pulleys and ropes all over the place. So I just want to quickly talk a little bit about tension and how it's working. The tension in a taut string or rope is a positive scalar number, which I call T, and it's measured in newtons. And one way I can sometimes try to think of it is I draw a table, and here's a pulley, which is like it's hard to draw, but you can draw a little circle. And I encourage you to try to draw these things. And then let's draw in black a rope, which is stretched over that pulley, goes all the way over here and goes down. And here's a mass M hanging on this side and a mass M hanging on this side. Can you picture it? And maybe, I don't know, this is like a table, which is tall, something. And so the question is, I guess, what is the tension in this rope? And one of the questions is that, it's probably either mg or it's 2 mg. And so that's kind of because there's 2 masses there. So, and I'll tell you the answer in a second here, because there's only one of those is right. If the string is wrapped over a frictionless pulley and we can neglect the mass of the pulley, then the string has the same tension on both sides of the pulley. So what happens here is that, right, and let's draw them in red, there's a force upwards on this mass of the tension. And there's a force upwards on this mass of the tension. And that's going to be the same, whoops, sorry, as the tension up here. Okay. And so you can sort of see, I think from the free body diagram that or force diagram that you draw of M here, is that you've got mg down and tension up. And so if acceleration is 0, then T equals mg. And so, and that's going to be true for the whole rope. So T equals mg is the tension for the rope on either side of the pulley and across the top. And I wanted to give you a poll about this. Here's a figure to the right. You got some, these could be unequal masses. The question is the tension in the string, which we'll call it right here, T, is it greater than, less than, or equal to the force of gravity on block B? So they're only asking about 2 things. The force of gravity on block B, which is going to be m sub b times g, and the upward force of tension. And it's a frictionless table up here. So this is, I'm going to launch a little poll, see what you guys think. Think about this one. Okay, what I want to do is quickly stop this voting and try again, because this isn't going so well. Sorry. Most people are saying equal to. So I do want to relaunch that in a second, but first I want to just say one more thing. I want you to think about whether or not B is accelerating. So when I did this one, the key here was that I said, okay, these are equal masses on both sides of this table. And so therefore, it kind of, that tension is going to be the same. They're going to support it. It won't accelerate one way or the other. 0 acceleration. So you got a frictionless table that's holding A. Is this entire system going to be accelerating, do you think? Okay, and then if you look at B, ask yourself, is there an acceleration? And if there is, there's got to be a net force. Let's just, anyway, the question, let's just do the same question, exactly the same question. Is the tension in the string greater than, less than, or equal to the force of gravity on block B? This is much better. Thank you. Let's give you just 10 seconds to click in on that, please. And then I'll draw it out. Okay, so and polling, share results. So some people have shifted from, a lot of people were answering question, answer A equal to. Now people are thinking that's less than. So what I think, the question that I asked you is, will the system accelerate? Yes. If it's a frictionless surface, then A accelerates to the right because there's an unbalanced force on it. and then B will accelerate downwards. Downward. So if I'm going to draw a force diagram for B, we can draw our little system thingy around B. It's just tension up and force of gravity down, MBG or something like that. Or I can just call it the force of gravity on B. Okay. And then I want to remind myself that the whole system is accelerating downwards. Okay. So I could define plus y is down if we want to. Then a sub x is positive, sorry, a sub y is positive. And then I would say that the sum of the forces is equal to the Fg on B minus the tension. And a sub y is equal to the sum of the forces in the y direction divided by the mass of B. You'd get Fg on B minus the tension divided by the mass of B. And you can solve that around mb times a sub y is equal to that force, right? The force that we're trying to compare, F gravity on B minus T, and you get that the tension is equal to m, sorry, that's again. It's that force GB minus the mass of B times the acceleration in the y direction. So this is going to be less than the force of gravity on B. Anyway, so it is C. So yeah, my point is that if it's accelerating down, you need an unbalanced force downwards, and so the tension's a little less. It's not always equal to mg. And that's sort of true for elevators or something. I think what I want you to do is start reading about the friction. I'm going to spend a lot of time on Friday talking about the friction force. Something to consider is, does friction always slow things down? Well, no. Static friction between your feet in the floor is in fact what allows you to walk. We talked about this before with James Bond. Walking certainly involves speeding up, and this would not be possible if you were on an icy lake or a completely frictionless surface that's covered in marbles. So that's kind of where we're going with that. I think what I'm going to do, I'm going to turn off the recording, then I'm going to take questions from you. So if you've got your hand up, I can talk more specifically about midterm related stuff if you have questions on that. Okay. Or the lecture is fine too. The end of all my YouTube videos is a big long pause while I try to figure out how to stop my recording. There we go. Be very dexterous with